Hey there, welcome back. Hopefully you've had some time to think about the progressive intersection function and how to implement WI. So let's jump straight into it. And as an example for how this can work, let's just go with ACBA, which is in there. And let's do let's say, XAC, and then a bunch of random characters. TRYU, sure, why not? Now, progressive intersection is going to be very similar to progressive membership, and actually I should have started with that, so let's cut that. So progressive membership is just the basic membership function over the tagging. And progressive intersection is going to be very similar, so we just do the intersection over the tagging. However, when we do this, obviously we still have the tags, so we need to get rid of them, and we can do that with a pick first. Gosh, it's not pick first, sorry, with a first each. And now we got rid of the tagging. So this is progressive intersection. And so we can implement it, or we can define it as PI, and it's just first of each alpha intersection over tagging of omega. And okay, there it goes. Progressive membership and progressive intersection are there. Now, what's next? Well, just implementing the whole behavior that I described. So let's see, do we have a guess underscore? We have. So what we need to do is we need to take into account the P is all of the positions that we care about right now. So we need to take the guess and we compress it with P. So this is what we need to compare with every other words, right? So now we're going to need to do a progressive intersection with these same columns, so this should be in closing parentheses. We need to compare this with the very same columns in sub. However, we've had a similar issue in the past. This is a vector and this is a matrix, and we want to apply progressive intersection to each each row of the matrix. So we need to pair this vector with all the vectors in here. So we do that with with a rank 1. And when we do this, these are the intersections we get. Now notice how things here were padded with spaces to make sure that we got a nice matrix with 3 columns. So actually, before computing the progressive intersection, after computing the progressive intersection, but before getting to this state, we want to do something else. So we want to take this. Sorry, these were fine, these parentheses are fine. What we want to do is take the progressive intersection here, do it as we're supposed to, but now we want to make sure that this is the same as the characters that we care about in here. And from these 4, the only one that we care about is this first one, because it's the only one that's matched with an A. So what we need to do is we need to take the guess here, and we compress it by the characters that were scored with a 1. And when we do that, we see that the first 3 elements got the correct intersections, and the other ones didn't. Now this thing here, this doesn't depend on the arguments, so this can be pre-computed. So we can call it, say, CM for the correct match, and then we can check if the correct match, matches that intersection. Now there's one subtle thing here that I'm making use of, and that I should mention just so you can think about it, and that is the guess is on the left of the progressive intersection for a reason. Because the thing I want to do is when I compute the correct match, so CM in this case it's just a single character, so it's not very interesting. But if I had, say, if my score were 1 to 0 1 0, now CM would be something else. Let's see, can I run this? CM would be AB. And it's AB because it's in the order of the guess. So it's this A and this B. Now when I do the intersection with 2 different vectors, for example, say I had a candidate word that was, let's say, well, this is not a word, but a mix of letters. An X, this is a B, This is a B, an A, and another X. If I do this intersection, or this progressive intersection even, with AB, not AB, ACBA, which is the thing we got from over here, ACBA, so actually this second B, this is already correct, so it can go. So if we have this, the progressive intersection returns a BA. Now this word is perfectly fine because it has an A and a B, and they're in different places, so this is a nice candidate word, but BA doesn't match AB. So when you have two vectors and you want to make sure that they have exactly the same values, regardless of the order, you need to sort them first before comparing them. However, the intersection primitive, the result is in the order of the left argument, and that's why we have a BA here, because the B appears first. So if I were to swap these two, now the AB appears first, because on the left the order is AB. Oh wow, actually I'm thinking, but I was thinking if, so what I said is correct, the order is the result, and so what I was about to say is that because we computed the correct match with respect to the order in the guess, we keep the guess on the left of the intersection, but actually I'm not sure if that's going to be enough for the result, because if this had, is this enough? Yeah, it is, because the ones, the numbers 1 are always on the left. Yeah, exactly. For example, if I had double B's here, or even if I had a B here and an A, but we were still selecting this B, but this wouldn't make sense, because this would be the B marked with a 1. So the letters marked with 1s are always on the left, and so yeah, this is fine. Yeah, exactly. So we keep the letters from the guess on the left, so that the order is defined by the guess itself. And so in the end, all things considered, the wrong intersections, those can be computed by taking the guess and the square and the and the score, and now computing the correct match, and that's the guess compressed by the letters that were scored a 1. And then we just do this whole expression, which goes in here, and we replace things. So sub is actually all of the words, and P was what? The score is different from 2. So now the PI is correct, we don't need a space here, and this is the guess. So now let's check our guess, our score, WI, and our words. Oops, what did I do? The guess and the score. Oh, I changed it later. So let's 12000 again, and let's see what we get. Oh, right, because I forgot to, silly me. After computing the Boolean vector, we need to filter the words, like in all other subfilters. So we fix that, and there you go. So that's WI, and now the function filter works because the 3 subfilters have been defined, and so we can take it for a spin. And we can see that no word, oh, actually 4 words, of all of the words, 4 words respect this guess and this score. So this appears to be working fine, and we are pretty much done. And in the final video, we're just going to play a random game of Wordle with these functions. So pat yourself on the back, you've done it. This was a great journey through Wordle and some nice APL functions, and I hope to see you soon. Bye.